Hey everyone, continuing our discussion through the units, we're going to move on to the next topic after forces, which is about energy, in particular, rotational energy. We've already talked about how there's all these different types of energies. We have the work being done by forces, we have the kinetic energy of motion, and the potential energy stored either through the form of gravitational or spring potential, things like that, and also heat. So we're going to talk about how such thing about energy caused by rotations. Now, we've been talking so far about how everything we've said that we've mentioned displacement, velocity, acceleration, force, mass all these have rotational versions of them. So the follow up question would is there a rotational equivalent of energy? So, what exactly would be the equivalent to rotational energy in the realm of translational linear type of energy? So, I mean, we could ask ourselves, well, there's a bunch of different potential energies. There's spring potential and there's gravitational potential. So maybe there's a rotational potential energy. Nope. The other type of energy that we have is kinetic energy, rotational kinetic energy, which we oftentimes will end up placing this as k rod. Now, this is going to be extremely important that at this point, now that we have two different kinetic energies, we will have to make sure that we subscript both of them. Just like how we had to subscript US and UG to represent spring and gravitational potential energies respectively, we're going to have to make sure that we clarify that an object doesn't just have k kinetic energy, but it has k rotational or k trans for translational kinetic energy. Now, if you want, you could set it so that k just by itself means the translational standard kinetic, and then if you're going to be doing rotational kinetic, you have k rod. But what comes down to is that you have to start getting to the habit of subscripting this kinetic energy specifically. Do not leave this as just K. Now, we can come up with the equation for the rotational kinetic energy the same way we've done with the other ones. In the realm of translational kinetic energy, we know that the equation is 1/2 mv squared. As we've talked about, we can kind of mix and match and take these translational terms, replace them with their rotational equivalent. The rotational equivalent of that is I for rotational inertia, and v, the rotational equivalent of that is omega, angular speed. So the k rotational equation ends up becoming 1/2 I omega squared. Right? Now, we could also have rotational work technically, because remember, work in general just means a change in energy. So obviously, we can have our rotational kinetic energy change. And just like we said before, with work being the force acting on an object to change its energy, we could kind of do the same thing where we replace the word work, with the term force with the term torque, and we end up getting the rotational work. Basically, the rotational work would end up being the torque that ends up resulting in a change in rotational kinetic energy. So once again, the work translational would be force times distance or displacement. The force gets replaced with torque, and the displacement gets replaced with angular displacement. All right. Now, I will just point out that this isn't really like its own separate type of work. This is really just the way work is done for a rotational aspect, but the main one is the kinetic energy. So here's the first question. Pause the video, work itself, and we'll go over in a second. All right. So they give us the rotational inertia, they give us the angular speed. We're just going to plug and chug into the equation, and we get our answer of 675 joules. All right, here's the next one. Pause the video, work itself, and we'll go over in a second. All right, so we're told that we have a 5 Newton force acting at the edge of a tire that's 3 meters, and we want to know what the amount of rotational work is essentially to rotate it one full revolution. Remember, one full revolution means 2 pi radians, because remember in the equations we have to keep this in radians. And torque is just going to be force times the radius, or the distance that it's acting at. So the 5 times 3, and then times it by 2 pi, and we end up getting 94.2 joules. All right, here's the next one. Pause video, work stuff, and we'll go over in a second. All right, so the way we're gonna end up doing this is first we have to figure out what the rotational inertia is for this system. Now, because the equation is 1/2 I omega squared. We can figure out what the angular speed is using this 30 RPMs, but we need to figure out what I is. They tell us that the rotational inertia is defined with this equation, 1/3 mr squared. So we're going to plug that in. We do need to make sure that we incorporate that each blade is 300 kilograms. So, triple that because it's a 3 blade turbine. So it's 900 kilograms. Now for the 30 RPMs, the way that we're going to end up converting it is by replacing revolutions with 2 pi, the minutes in the RPMs with 60 for 60 seconds, and that's how you convert from RPMs to radians per second. All right. So plug it all in, and we end up getting 1.33 times 10 to the 6 joules. All right. Here's the next one. Pause video, work cell phone, we'll go in a second. All right. Here, they want us to figure out what the change in kinetic energy of the pulley is. So what we're going to do is basically kind of recognize the idea that change in energy is work. The reason why we can't just do straight up change in kinetic energy is because we don't have the angular speeds at any point. But we do have the force, the distance, which can help me find torque. And I do know the number of rotations, 3 full rotations. So I know the angular displacement. So clear indicator that I'm going to want to do the rotational work. Remember, one big tip is if you're, try to consider asking yourselves if this was asking me just, not rotational aspect, just asking what's the change in kinetic energy. How could I do it with this information? You might realize, oh, I could do work, and then just kind of again replace all the linear terms that you would have used with the angular versions. So this ends up becoming just FR times theta. Plug the numbers in. Because it's 3 full rotations, we have to take the 2 pi, which is the number of radians for one rotation, and times it by 3, and we end up getting 226.2 joules. All right, here are the next two. Pause the video, work cell phone, we'll go in a second. All right, so they want us to figure out the final angular speed. Now we know that the object, well, it doesn't say that it starts at rest, but it was supposed to say that. So in order to find the angular speed, we can use the work, and we know that the work is equal to the change in kinetic energy. That was what we just found before. The initial rotational kinetic energy was 0, so this change in kinetic is just going to be equal to the final rotational kinetic energy, which is going to be equal to 1/2 I omega squared. And we can plug in the rotational inertia of the pulley that they gave us in for I. So our equation, when we plug all the numbers in, will get us the angular speed to be 6.73 radians per second. Then to find the final linear speed at the edge of the pulley, we could then basically use the linear equation that relates the angular speed with the linear speed. Basically just multiply this by the radius in order to remove the radians and turn it into meters. So we take this number, multiply it by 2, and we get 13.45 meters per second. All right. I believe this is the last one, so pause the video, work cell phone, go in a second. All right, so they want us to figure out how far they would have to run in order to get the merry-go-round to, go to this final speed. So what we're going to do is basically do a combination of what we did in the previous question. We know that the amount of work that we do, the rotational work, is going to be equal to this change in kinetic energy. We know what the change in kinetic energy is going to be. So what we're looking for is the theta, the angular displacement. So we're going to take the I guess the altered form of the rotational work equation, FR times theta, and we set it equal to the I, 1/2 I omega squared, and then replace the I for the disk with 1/2 mr squared. Put all the numbers in and chug out an answer, and we get 2.817 radians. Now the problem is this is not what they're asking. They want to know how far they actually traveled, they ran. So we're going to have to convert this angular displacement into linear displacement again by using our conversion equation, multiply it by the radius, and we end up getting that they ran a total of 5.63 meters.